everyone, and welcome to today's webinar on network cabling. My name is Priya, and I'm the marketing lead. Before getting started on the webinar, a few reminders. This webinar is being recorded, and we will send you the link to the recording in a couple of days. This will also be up on the website. So please feel free to share the link with your coworkers, or if you want to rewatch it again. During the webinar, if you have questions, please put them in the chat box or in the Q&A box. And today's topic is presented by Rich Whitty, Sales Manager here at Vitex. Rich graduated from West Point in 1987. After serving in the Army, Rich embarked on a career selling capital equipment to the semiconductor industry. He has many years of engineering experience and joined Vitex last year. Now over to Rich.
Hi, everybody. Thanks for joining us today. I appreciate the opportunity to meet with everyone. We'll talk today about high density intra and inter-rack cabling considerations. Let me go ahead and pull up my PowerPoint presentation, and we'll begin shortly. Okay, can everybody see the screen?
Yes, we can see it. Thanks, Rich.
Okay. Okay, so we're basically in a situation where you've got a lot of data centers and a lot of enterprise network people migrating to 400G in their core. And so there's some cabling considerations and trade-offs that people are considering. And most of that has been direct attached copper versus active optical cable. There seems to be a new player in town called the AEC, which is active electrical cable, which takes a place a little bit or pushes the boundaries of a little bit of both of the other options. And at this point in time, I'd like to talk about all three. And you can chat with any questions, but probably save the questions until the end, if that's okay. So here's a nice picture of a data center. So we're going to talk a little bit about you want to increase space utilization while decreasing operating costs. And so there's a number of trade-offs that you have to consider. One is data rates. We're just going to go ahead and assume, we're going to be given a data rate that we're operating within. So we're not gonna actively look between different data rates or bandwidths. We're just going to go with 400 gig because it seems like that's the latest core migration. We're going to talk about real estate, meaning gauge or thickness, and that will affect bending radius. And then we're going to talk a little bit about reach or maximum distance. And it may not be directly applicable to intra or inter-rack cabling, but it's an important consideration for other things within your data centers, whether you're going from the leaf to the spine or any other cabling considerations you might have. We want to talk a little bit about power budget. Of course, if you're in a data center, this is a huge parameter. And then we're going to talk briefly about latency. On my next slide, I'll talk about that a little bit. And lastly, we'll just qualitatively talk about costs, not quantitatively. But if you have any questions about cost, I'll be more than happy to answer them either after this, or we could talk face-to-face at a later date. One of the things about latency, and I'll just start out with this, it may be less of a consideration for some people if you're doing sustained transfer of data. But if you're talking about like high performance computing or neural networks or supercomputers, you basically have a lot of transactional data queries. So if you're about latency, it can really, it's not just the latency of your switch or your network interface card, but it's also the latency of your pluggable. And when you're talking about connection paths, especially with transactional data queries where you have to query something, wait for an answer, and then process it, and you're doing parallel processing, all those latencies add up. And if you take a look at the graph to the lower right, you can see this graph just shows the links in a connection. If you just look at 3 links at 20 nanoseconds, with maybe a switch and a network interface card, you might be talking about 150 nanoseconds. But if you talk about 100 nanosecond latency for let's say an AOC, and you add that up between 3 connections, you can very quickly get up to over 600 nanoseconds. So just wanted to share that with you. You can see how the latency is additive or summed. Okay, we're going to start with direct attached copper, and I figured we'd start out with the 400G. I don't know if you can see me. This is a 100G direct attached copper, and if you can see the thickness, it's about as thick as a number 2 yellow pencil, and it's fairly heavy, or it's a lot heavier than something per se that looks like this, which is an AOC, which has OM3 or OM4 fiber optic cabling at a lot thinner diameter. So your passive copper cable, there's no signal conditioning, there's no clock data rate or retimer. It just basically takes your electrical signal coming from your host, which is NRZ modulated and just has contact pads and does direct path through. So the signal is attenuated quickly, so you're somewhat limited to length because of signal attenuation. We could talk about that a little bit later. With 400 gig, we're also going to be more limited by the thickness and bending radius of the copper cable itself, as opposed to signal attenuation. You're looking at, for power, 1.5 watts per cable end. As far as power is concerned on the direct attached copper, very low power consumption. And in terms of your diameter, you're looking at, for 400 gig, you're looking at 28 AWG for a 2-meter cable, or even a 3-meter cable. And that's 0.08 millimeters squared diameter. And just for reference, because we're going to talk about a 32 AWG gauge later, the 28 is 2.5 times larger in diameter than a 32. So just a point of reference for those of you who are not fluent with AWG. Okay, the next thing I want to talk about is the AEC. This is a 400 gig AEC, and if you can see it, it's a lot thinner than the 100 gig DAC cable. Kind of hard to tell, but it's about half the diameter, and it's 4 times the bandwidth. The way this operates is you're taking your electrical signal and you're doing signal conditioning. We have a system on a chip, a mixed signal ASIC chip with a clock generator. Basically, when we plug this in to the host, we'll plug it in on both ends, but it calibrates amplitude and phase at the startup, and basically comes up with what we'll call a golden standard for the eye, the open eye or the wide eye. I'm sure people are familiar with eye diagrams, but that's basically looking at the PAM4 modulation scheme and taking a look at what they call an eye diagram for that. During calibration, the chip looks for an optimal sampling point, and it looks for the largest openings in the eyes at a certain clock phase. Once it gets that golden standard, it basically pulls environmental inputs that are also on the chip, i.e. temperature, and it'll adjust the circuitry on the receiver end to improve the eye, so it's always looking at the optimal sampling point. So this thing's self-testing, retiming, optimized. self-test, retime, optimize. So this thing is always looking for the best I, and therefore looking at the best BER, if you're familiar with that term. The latency on the AEC is actually pretty good. It's 4 nanoseconds at 400G. The power consumption is 5 watts per cable end, so 10 watts for a cable. When we talk about thickness, remember we talked about a 28 gauge earlier. For very short throws or very short reaches, we're talking about 32 AWG, and that's 0.032 millimeter square diameter. That's about 40% of that same gauge as it was for the DAC cable at the same length and at the same bandwidth. Now, if you want to go a little bit longer and you want to go 5 meters, you can see that the gauge is going to go down, thickness goes up to 30. And if you want to go a full 7 meters or 21 feet, you're going to wind up being the same as a very short throw for a DAC. You're going to wind up at 28 AWG. If you look at 2.5 meters and below, we're talking about interconnect densities of 500 cables per rack. So a lot of space savings. You're really optimizing your space with the AECs as compared to the DACs. Want to talk about lengths or throws. We talked a little bit about it briefly prior, but you can go up to a max length of 7 meters with the AEC as currently configured. Bit error rates we talked a little bit about earlier through the calibration of amplitude and phase, and then actually adjusting the circuitry based on environmental inputs. Bit error rates are 1E15 post-FEC, and pre-FEC is 1E8, and that is actually at 7 meters. It gets better if, of course, if you talk about shorter throws, but I wanted to throw a worst case scenario at you for bit error rates. As you can see, they're very competitive and very good. In terms of the circuitry itself, you're talking about 8 lanes of 50 gig PAM4 modulation. Of course, on the host side, it's NRZ. And we also have a digital diagnostic monitoring over I²C, and it's CMIS 3.0 and 4.0 compliant. You basically have to let us know which one you want, as they're not compatible with each other. One is not reverse compatible. The 4.0 compliant CMIS is not reverse compatible with the 3.0 CMIS. Here's basically the system on a chip, or the mixed signal ASIC that we were talking about. I'm not going to delve into this too much, but you basically have one clock generator for 4 lanes of application. You've got your retimer on each lane, and you can take a look at the phase generator and the phase rotator. Basically, you go in, you take a look at that. That's how you do your bit error rates, by clocking into that, selecting your golden eye, and changing that in comparison with kind of what I would call a lookup table on the humidity inputs. So just a little something to think about. If you have any in-depth questions on this, I'll be happy to answer it at the end of the presentation. Okay, this is just a little bit about taking a look at the clock phase. This is, if you can see my pointer, I look into optimal sampling point. We're looking at a sampling point. This is NRZ. It is not PAM4 modulation, but it's just a better way of showing or demonstrating what we're looking for. We're looking at the appropriate phase where we get the widest I available, and therefore the best signal without any crosstalk, or what I'll call, we have high signal to noise at this point. And so that's our golden eye picture. Once again, this is NRZ, not PAM4, but it gives you an idea of what we're trying to do. And that's how we maintain such good bit error rates. Let's talk a little bit about active optical cable. It basically takes an electrical to optical Same thing as when you talk about pluggable transceivers, it's just already attached with an OM3 or an OM4 cable. Latencies are very good with these products. We have two different types of products. One is an analog CDR chipset, and one is a digital signal processing chipset. The latency is far better with the analog chipset at 20 nanoseconds, and it goes up to a little over 100 nanoseconds latency with the DSP. Once again, remember that all the latencies are additive. So if you're doing a lot of transactional data swaps, you probably really want to look at either the AEC or the analog chipset for the AOC. In terms of power, if you're taking a look at the analog chipset, it's 7.2 watts per cable end. And if you want to look at the DSP, it's 8.8 watts per cable end. And that is, of course, because of the power overhead for the chip itself, for the DSP chip. And in terms of length, if we're talking about intra and inter-rack connections, it's probably a non-issue. But, you know, we could do 100 meters and on OM3 and even 150 meters with OM4 with the AOC. In terms of FEC, it's got a very robust FEC. It's KP4 FEC with PAM4 modulation. And once again, digital diagnostics monitoring over
I think
I wanted to.
Hey, Rich,
I'm
sorry to interrupt. I think we were having a bit of connectivity issues. Yep, you can go on now.
Okay, sorry about that. I want to talk a little bit about the architecture for the analog CDR, as that is kind of a special AOC that we here at Vitex offer, as well as the DSP. But the way we do analog CDRs is that we actually increase our apertures and increase spacing between the transceivers, transmitters, I should say, pixels. I have.
Hey, Rich. So we're still having some connectivity issues. So,
Just a higher.
Rich, can you hear me?
A higher stable. Hey guys, I apologize about the technical difficulties. We're actually increasing our office space, and we're having some work on the office space next door, and that may be interfering. That may be interfering with our ability to connect. So I apologize about that. With everyone's permission, I'll just go ahead and go back to the PowerPoint presentation.
Yep, we can hear you now. Yeah.
Thanks. Okay. So basically what we've done is we've used our experience in video over fiber to create a new platform for these VCSELs that on a DSP, basically you got a singlet VCSEL with 4 VCSELs that communicate. That's max lens diameter of about 250 micron. And you're looking at, we have a max lens diameter of 400. So we have a lot more real estate. We also space them wider apart. So it lowers optical crosstalk between channels. We have a self-aligning, what I'll call a jig, but basically the way we manufacture these, everything's plug and play and self-aligning. So we have negated the need for ferrules. So, we're just going through air. We're not going through glass. So there's no reflection. There's no refraction. It's a better quality beam and a smaller spot size. With this, we can get around using a DSP chip, and we use an analog CDR chip, which is cheaper to manufacture, and it also cheaper to manufacture, and it also has a lot less overhead in terms of power constraints. All right, go to the next slide. Oops. If you take a look on the left, that's an open eye diagram. The left and the right are open eye diagrams for PAM4 modulation. If you took the single VCSEL type of architecture and you didn't use a DSP chip, the eye diagram would look like it does on the left. The eye diagram on the right is actually taken with an analog chipset, but it also would be indicative of you using the singlet with a DSP. The eye diagrams are very similar, but once again, if you use the analog, you can save on cost and you can save on power, and you get better signal to noise. Okay, in conclusion, some of the things we look at, some of the parameters we want to look at are data rates. The DACs at this point in time, they offer all the data rates. We've got 10 gig DACs, we've got 10 gig AOCs. The AECs, we've got 200 and we have 400. In terms of the direct attached copper, it really depends on the data rates, but you're talking at most 3 meters, but there's some wiggle room in there where 3 meters actually might be a little too much, because the cable diameter gets so thick you can't stuff enough cables into the back of your rack appropriately. The AOCs, 100 meters on OM3, 150 meters on OM4, and the AECs will have a max distance of 7 meters. Most of the time, you're going to be using 2.5 meter or 3 meter cabling for the AECs, inter and inter-rack. Fairly intuitive that the direct attached copper is going to use copper. The active optical cable is going to use optics and fiber, and the active electrical cable is going to use copper. You talk about weight. Of course, the DACs are really heavy. The AECs are in the middle, and the AOCs are extremely light. But realistically, what you're worried about is the bending radius and not really the weight. And so once you get these big heavy cables like the DACs at 400 gigs, they get so heavy and so thick, you really can't bend them appropriately to optimize the amount of cables that can go into the back of your servers. Most importantly, for some people, are going to be cost or money. DACs are considerably cheaper. They're under $100 a pop. You're going a little bit above 200 for the AECs. And depending on what kind of AOC, you talk about slightly more for the AOCs. So just from a qualitative standpoint, $1 sign, $2 sign, $3 sign. In terms of diameter, we talked about this a little bit earlier. For the DACs at 400 gig, you're talking about 28 AWG. That's going to be 2.5 times the diameter of the AEC, so 2.5x, the AEC being 32 AWG, equaling X, and the AOC being so small, I just wrote non-applicable. I mean, I think all of you have seen what fiber optic cabling looks like, and it's very bendable. It's got very good bending radiuses, and you're not going to have a problem populating the back of your racks or your servers. Latency, and once again, this may not come up as a consideration for everyone, but if you're in high performance computing or have transactional data queries, it's certainly going to be of interest. Your DACs are going to be kind of non-applicable. There's not a lot of overhead in that. The AECs, you do have system conditioning, and you are looking at that certain phase where you want to take a look at your OpenEye diagram. So you got about a 4 nanosecond latency with the mixed signal ASIC. And on the AOCs, when you talk about the non-DSP or the analog chip CDR, you're talking about 20 nanoseconds. And if you're talking about a DSP AOC, you're talking a little over 100 nanoseconds. So with that, I wanted to thank you for being so patient, especially with our operating difficulties with connectivity. And I will take any questions if you have them.